Hello, my name is Josef Horák and I'm the Senior Application Specialist at NenoVision. Welcome to the second webinar in the Coffee Breaks with NenoVision series. This time we'll be talking about the advantages of combining AFM and SEM systems for 2D material analysis. And of course, we'll be glad if you will stay with us for the whole webinar series. So we always stream on the same day, only 1 week apart. And the next one is happening on July 9th and is dedicated to combination of AFM with focused ion beam SEM systems. And just to remind you that in this streaming format, you can only ask your questions using the Q&A chat window. And since these slides are pre-recorded, I can answer your questions during the stream. And if there are going to be any important questions, I will answer them by the end of the webinar on microphone. And today we have there one more thing. In the Q&A chat window, we have there a link where you can leave us a feedback that will help us a lot to get better. So with that, enjoy the presentation. Welcome to today's presentation focused on the advantages of combining AFM and SEM systems for characterization of two-dimensional materials. When we think about the properties of a material, we often think that they are based on what the material is made of. However, there is something else that can affect how a material behaves, its size. This is especially true of some materials when their dimensions are reduced to the nanoscale. There are many materials that acquire unique properties if their size gets reduced to a single atom layer, and one can further tune those properties by controlling the physical dimensions and their chemical composition. To name the important ones, electrical conductivity from insulator to superconductor, mechanical strength, and interaction with light. So introducing these modifications either intentionally or unintentionally in the form of various defects requires tools that can precisely evaluate the structural, electrical, and other properties and relay them with the desired functionality. And this is where connecting the AFM and SEM as two of the most used complementary techniques for sample analysis in the nanoscale becomes crucial. The two-dimensional materials will be defined in this presentation as follows. Only if the material possesses one nanoscopic dimension, it will be considered as a 2D material. Nevertheless, some application examples in this presentation will show combination of 0, 1, and 2-dimensional materials. So what is actually LiteScope and the AFM and SEM approach? LiteScope represents unique atomic force microscope, which is designed to be easily integrated into a variety of scanning electron microscopes. And in the following slides, I will explain all the benefits coming from the atomic force microscope and scanning electron microscope connection, this time with focus on 2D material analysis. Why to actually combine AFM and SEM systems? Atomic force microscopes and scanning electron microscopes are two of the most used and in fact complementary techniques for sample analysis in the nanoscale. Nevertheless, since the principle with which they observe and interact with the sample surface is completely different, they provide very different set of information. AFM monitors an interaction between a physical probe and sample surface, and for that reason represents a tool of choice for topography and roughness measurement with sub-nanometer resolution. AFM also enables analysis of mechanical, electrical, and magnetic properties. On the other hand, scanning electron microscope observes and analyzes the sample surface using a focused beam of electrons. This interaction produces various signals, so besides fast 2D imaging in wide range of resolutions, SEMs can provide information on sample composition as well. Further possibilities of SEMs, such as surface modification or nanomanipulation, will depend on their additional accessories. With that being said, the motivation behind LiteScope design is as follows. First of all, the AFM and SEM systems allows for efficient yet complex in-situ sample characterization that combines capabilities of both techniques. And second, it brings completely new possibilities for advanced correlative imaging which allows analyzing samples in a way that was difficult or impossible by separate SEM and AFM systems. Let's have a quick look at an example of tungsten diselenite flake placed over silicon pillars. In the left, there's an AFM image showing three-dimensional topography. On the right side, there's a SEM image of exactly the same structure that provides great material contrast. And in the middle, you can see the correlated image using NenoVision CPAM technology that clearly provides more information about the sample that would have otherwise been possible using each imaging modality separately. CPAM stands for Correlative Probe and Electron Microscopy, and let's have a look on how it actually works. On the sample, the electron beam points close to the AFM tip with a constant offset. And during scanning, the AFM tip and electron beam remain static. Sample is being scanned only by the LiteScope piezo scanner. And this enables simultaneous detection and acquisition of AFM and SEM signals at the same time, in the same place, and under the same conditions. And this technology is unique to LiteScope and was developed for seamless data correlation. The possibility to record both AFM and SEM channels at the same time is shown here in NanoView software. You can see analysis of graphene flake in 6 different channels. The SE and BSE signals come from the SEM, and 4 channels, topography, energy dissipation, and frequency shift, come from LiteScope. Also, the video shows precise AFM tip navigation to the area of interest and control over the scanning process in the SEM view. Of course, the choice of the appropriate channels will depend on the application and on the user. The ability to image sub-nanometer structures is an important prerequisite in the field of 2D materials. This slide shows LiteScope performance on a silicon carbide test sample with individual step height of 750 picometers. LiteScope detects the step height precisely with approximately 50 picometer error, and the surface roughness of this sample was established to 180 picometer root mean square. The following 4 categories will demonstrate why is the combination of AFM and SEM together with correlative CPAM technology advantageous for 2D material analysis. Firstly, using SEM to localize the specific structure and to navigate the AFM tip to that structure can be crucial for successful sample analysis. Then both SEM and AFM complement each other in identification of individual layers of multi-layered 2D materials. Also, the AFM and SEM approach allows for comprehensive sample analysis, including, for instance, material contrast and chemical analysis in combination with materials' mechanical and electrical properties. And lastly, the fact that AFM and SEM rely on completely different imaging strategy enables analysis of heterogeneous materials and structures, where using of just one technique wouldn't be insufficient. So to put it simply, SEM enables to look into the material, while AFM can detect even the smallest topographical change. And in the following slides, I will go through each category one by one and will try to show the above mentioned key advantages using specific applications. Let us start with the most straightforward feature of combining AFM and SEM. SEM possesses a wide range of resolutions, which enables fast localization of the region of interest and fast AFM tip navigation to that structure. And for that, I'm going to use application where we did quality analysis of graphene growth. Here, graphene was prepared by thermal decomposition of silicon carbide, which is a temperature-sensitive process, and as a result, the final quality of graphene layers may differ across the sample. Thus, precise identification of the region of interest on the sample was crucial. And using the LiteScope in combination with SEM allowed comprehensive study of graphene growth in relation to the sample topography, because graphene layers start to grow from the edges of silicon carbide substrate. So besides easy and fast localization of the region of interest on this sample, the different imaging capabilities of AFM and SEM help to provide more complex analysis than both techniques could provide separately. The SEM images clearly provided beautiful material contrast of graphene layers, which is something that would have been much harder to interpret in the AFM topography. On the other hand, AFM relates direction of graphene growth to individual silicon carbide terraces, and CPAM technology connected both datasets into one image for unmistakable data interpretation. The field of two-dimensional materials has expanded to a multi-layered system in which electronic, optical, and mechanical properties change, often dramatically, with stacking order, thickness, twist, and interlayer spacing. The AFM and SEM approach provides perfect tool for analysis of multi-layered materials. For this purpose, I'm going to use application where we studied multi-layered tungsten diselenide flakes laid over silicon nanopillars. A certain shape of the tungsten diselenide monolayer over the nanopillars creates a single photon emitter, as shown by this photoluminescence overlay image. Flakes that were showing the desired properties were identified by SEM and subsequently imaged by SEM and AFM at the same time using CPAM technology. Here the AFM topography served predominantly to expand the 2D SEM material contrast into third dimension, which is of particular advantage when analyzing such a complex sample that in fact represents combination of 1D and 2D materials. The CPAM image clearly shows advantages of combining SEM and AFM. Merging the SEM material contrast with AFM's monolayer resolution helps to visualize and understand how the flakes cover the nanopillars. AFM in SEM approach provides multimodal imaging of both chemical and physical information in high resolution. The combined systems enable local correlation of material properties with chemical makeup, making fundamental questions of how chemistry and structure drive functionality of 2D materials. Among the many unique and attractive properties of 2D materials, mechanical properties play an important role in manufacturing, integration, and performance for their potential applications. In this application, material contrast, topography, and local mechanical properties of graphene membrane were investigated by energy dissipation. In short, energy dissipation technique primarily enables to identify softer and harder areas on the sample. And to be able to interpret the data clearly, it was useful to correlate mechanical properties with material contrast provided by SEM in form of BSE signal and compare the correlated image to the AFM topography. In this application, the local electrical characterization was performed on a heterogeneous sample, which contains small structures of graphene and a specific derivative of graphene on a graphene oxide substrate. The AFM and SEM approach enabled to identify these structures, and using the AFM cantilever as a nanometer scale contact, the conductivity differences were measured with nanometer precision using current voltage characteristics. IV spectroscopy provides a plot of the current as a function of the tip bias voltage applied to the sample, and LiteScope supports bias of -10 volts to +10 volts. As depicted in the measurement, the graphene structures, represented by the red curve, were more conductive than the graphene derivative, which is the blue curve, and graphene oxide, represented by the black curve, was non-conductive. In this last application example, graphene was used for surface enhanced Raman spectroscopy, shortly SERS, boosting the Raman signal for ultra-sensitive analytical applications. This application falls within the category of 2D but also 1D materials. It represents another example where the connection of AFM and SEM complements each other. Analysis of such sample would be difficult by separate SEM and AFM techniques because SEM provides contrast only on golden nanoparticles, while AFM can easily visualize the graphene coating, but on the other hand, generally struggles to image small spherical objects. So the CPAM image, combining both techniques, clearly visualizes both the particles and the graphene coating. Let's summarize the key advantages of LiteScope as an AFM and SEM hybrid system for 2D material analysis. First of all, the possibility of multimodal sample characterization combining analysis of both chemical and physical properties is essential for optimization of 2D materials production process control and defect localization. And as we've seen throughout the presentation, for the analysis itself, the SEM grade material contrast is complemented by the LiteScope's three-dimensional topographic imaging with monolayer resolution. Then, the CPAM technology can precisely correlate various AFM and SEM channels into one image, which in some cases can be crucial for correct data interpretation. And additionally, in-situ conditions ensure the complete analysis under the same conditions with minimal sample handling. And lastly, because of structural properties of 2D materials, SEM's wide range of resolutions plays a key role in identification of the region of interest on the sample. And with that, I would like to thank you for your attention. Dear all, thank you for your attention. And as always, we are starting the Q&A section. So we have collected a couple of interesting questions that we would like to answer this way. So the question number one is, which kind of mechanical measurements can you perform on 2D materials? And is it possible to analyze not suspended membranes? So we offer several AFM modes to provide sample characterization of mechanical properties. We can measure local elasticity, stiffness, and using, for instance, force distance curve measurement, you can analyze further possibilities on your sample. And is it possible to analyze the not suspended membrane? Yes, of course, you can easily measure membranes or 2D materials which are not suspended. Question number two. Can you measure Kelvin probe force microscopy on graphene? Do you have any examples? And I would be interested into this application. Yes, you can measure KPFM to provide information about local surface potential. And graphene is one of the material which we have already analyzed, and we can share more details about this application. But please, it would be good if you would contact us directly over email. And the last question is, what accelerating voltage which was used for observation of gold nanoparticles covered by graphene that you could see through? Did you try another materials? So for this application, we have used 20 kilovolts accelerating voltage, but most probably even much lower accelerating voltage would be sufficient. I think that some of our customers use that, but this was the only application of this kind we have done, at least as far as I remember. So with that, I would like to close the Q&A section. And once again, I would like to invite you to the next coffee break with NenoVision that is dedicated to focused ion beam application, AFM and SEM. And that one is streaming next Thursday. And once again, please, it would be good if you would give us the feedback in the questionnaire that we have posted in the Q&A section. And once again, thank you again so much for your attention. And on behalf of the whole company, I would like to thank you again and see you next time.